Hi students, in this video we are going to determine the Fourier series coefficient AK. So in the last class we have discussed about the Fourier series representation of a sine and cosine signals. So the previous method of finding the Fourier series coefficient is possible only when x of t is represented in terms of sine and cosine. Hence we need a method that will determine the Fourier series coefficient for any arbitrary periodic signal. So for that purpose we are going to derive some relation, and from that relation we are going to determine the Fourier series coefficient. Okay, now consider we have discussed about this equation, right? Any signal x of t can be represented as, that is in terms of exponential Fourier series. Okay, so summation k equal to minus infinity to infinity ak e power j k ohm naught t. Now here what we are going to do is we are going to find out this coefficient ak. Okay, so for that we are going to do some derivations here. So what is the thing first we are going to do is consider this equation, multiply by e power minus jm ohm naught t both side and integrate with the limit 0 to t. So here I have done multiplied by e power minus j m ohm naught t dt and integrate to 0 to t. Similarly left side we have to do in this manner. Okay, so I have done it. Now consider summation k equal to minus infinity to infinity ak. Now combining these two I will get e power j k minus m ohm naught t into dt. Okay, now in this we are going to consider this part alone, and we are going to analyze something. What is the resultant we will have when k equal to, when two condition, when k equal to m and k not equal to m. We are going to analyze these two condition. Now consider this equation 0 to 2 e power j k minus m ohm naught t into dt. Now when both are equal, right, both are equal means here k equal to 1 m equal to 1 I have taken. Here when you take this, what it will become, it will become 0 ohm naught t dt. So e power 0 is 1, so you will get integral 0 to t dt. So when you integrate integral dt you will get t, then we apply the limit 0 to t, you will get the answer t. Now consider not equal to case, you can take any value. K, here I have taken k equal to 2 and m equal to 1. Okay, so in this what I have done is e power j 2 minus 1 ohm naught t dt I am getting. So 0 to t e power j ohm naught t dt. When I integrate with respect to t, I will get this coefficient at the denominator. So e power j ohm naught t divided by j ohm naught integral 0 to t. Next I need to substitute the upper limit and the lower limit. Before substituting here we are going to consider this part. We have already know the equation, that is the fundamental period t equal to 2 pi by ohm naught. From this ohm naught t can be represented as 2 pi. Okay, so now I am going to, wherever I am having 0 to t I am going to have 2 pi. Now if we want to integrate this, I need to I simplify this. I need to apply the limit capital T for z small t and 0 for small t. Now applying the limit, what we will get is e power j ohm naught t minus e naught j ohm e0, that is e power j. For ohm naught t I am substituting 2 pi, e power 0 is 1, so I have substituted here. So here e power cos can be written as cos 2 pi minus j sin 2 pi. Okay, so this is equivalent to, this is equivalent to 1. So here you will get 1 minus minus 1 divided by j ohm naught, which is equal to 0. Similarly if we find for different conditions, here what you will get is you will get 0 to t for this integration. If k equal to m, the answer is t. If k not equal to m, the answer is 0. This is what we are analyzing here. This is what the inference we made from this integration. Okay, so now what we are going to do is, already this is we considered the first, considered this equation. So what we did is we have considered the equivalent for this alone, right? Okay, similarly here we have considered for this alone, for this equation alone. So we have find out for this alone. Right now we are going to equate these two. Just for instead of this, I am going to substitute the equivalent value. So this is what the thing we have find out. This is the thing we have find out. Now I am going to substitute the equivalent value at this place. Okay, so here what I am doing is the same thing I have written, 0 to t x of t e power minus j m ohm naught t dt is equal to ak. Here instead of this I am going to substitute this condition, t for a k equal to m, 0 for k not equal to m. Here we are not going to consider summation because we are going to find only the ak coefficient, because in that equation itself we are having k, so we can put the values we can find out the coefficient by substituting the values k equal to 1 2 3 like that. Just we are not going to perform summation, we are going to find out the coefficient only. Okay, so here this therefore this ak from this equation, by keeping this ak here, 1 by t can bring downwards. So 0 to t x of t e power minus j m ohm naught t. Instead of this m, here I am substituting k because k and m are equal. Okay, so this equation is known as synthesis equation because it is used to synthesize x of t from ak. Okay, and this equation is known as analysis equation because it is used to analyze x of t and reveals the frequency content of the x of t. Okay, so here in this equation when you substitute k equal to 0, what you will get it, 1 by t integral 0 to t x of t dt. So this, if you want to find out the dc component, we need to substitute k equal to 0. So this is what the equation you need to know in order to find the Fourier coefficients for any arbitrary periodic signal. Now we will see a problem related to this. Now consider this problem. We need to find the Fourier coefficient of the signal. They have given one signal. Normally if they have given in terms of sine and cos, you can easily represent in terms of e power j. Okay, so but here square wave we may not able to represent in terms of e power j. So for that we are going to use this synthesis and analysis equation to represent any signal in terms of its exponential. That is the significance of the Fourier series. Now in order to find out this x of t, that is we need to represent this, that is x of t is equal to my infinity to infinity ak e power jk ohm naught t. Okay, thus this is your original signal x of t. I am going to represent this signal in terms of exponential. Now here in order to represent this you need to know ak. So now I am going to find ak equal to 1 by t integral 0 to t x of t e power minus jk ohm naught t dt. So this is the formula we are having. Before that here you need to substitute x of t value for this formula. So the first step is you need to represent this x of t in terms of the mathematical expression. You need to write it. Okay, so this x of t, what we need to do is, you know how to write down the mathematical expression. Since it is an periodic signal, it is enough to represent for one cycle. So this is what your one cycle. Okay, so what I am going to do is, this is the amplitude 1, this is what one cycle, right? This is represent one cycle. So 1 for t less than or equal to minus 1 by 4 less than 1 by 4 here, then minus 1 for 1 by 4 less than t less than 3 by 4. Okay, 1 by 4 to 3 by 4 minus 1 by 4 to 1 by 4. Okay, so now using this I am going to represent this. Therefore ak can be written as 1 by t. So I am going to split this integral. One is from, what is the value, minus 1 by 4 to plus 1 by 4. What is the value of x of t in this equation? I am going to take this equation. X of t is 1 e power minus j k ohm naught t dt plus 1 by 4 to 3 by 4 minus 1 e power minus jk ohm naught t into dt. Okay, so this is what the thing I have represented. Okay, the next step is, we know that ohm naught t equal to 2 pi, right? here first thing is we need to find out ohm naught equivalent, we need to substitute here. Now find out the what is the fundamental time period. The fundamental time period is this one, this, right? So what is the fundamental time period? 3 by 4 minus of minus 1 by 4. So this is the limit, upper limit minus lower limit. So what you will get here? 3 by 4 plus 1 by 4. So here you will get 4, 3 plus 1, which is equal to 3 plus 1 by 3 plus 1 is equal to 4 by 4. So your resultant is 1. So T equal to 1 in this case. So therefore ohm naught into 1 is equal to 2 pi. Okay, so wherever you are having ohm naught, now you need to substitute 2 pi. Understood? So here we have find out the value. Otherwise you remember this, ohm naught is equal to 2 pi by t. So wherever you are having ohm naught, you need to substitute 2 pi by t. So here 2 pi t is 1, so I am going to substitute ohm naught is equal to 2 pi. So in this equation I am going to substitute ak equal to 1 by t integral minus 1 by 4 to 1 by 4 1 e power minus jk 2 pi into t dt plus integral 1 by 4 3 by 4 minus 1 e power minus jk 2 pi into t dt. Next I am going to integrate this. Similarly for this t also you substitute 1 because the time period t equal to 1. Now here integrating this and substituting the limit, you are getting this answer. So simplify this. Okay, so here I have taken minus j downwards. When you move in the numerator, it will become plus j. Okay, so here simplifying this, e power minus jk pi by 2 e power minus jk pi by 2. Here minus is common, so e power minus jk 3 pi by 2 minus into minus plus e power minus jk pi by 2. Okay, so here I have taken e power minus jk pi by 2 outside, 2 minus e power minus jk pi minus e power jk 3 pi. You can stop up to this, that's enough. Okay, so here this is I need to find out for k. Okay, here when k equal to 0 I need to find out the value. So if it is k equal to 0, the formula is a naught is equal to 1 by t integral t 0 to t 1 by t integral 0 to t x of t dt. You should not substitute k equal to 0 here. Okay, so here if you want to find out the dc component, you need to use this equation. Okay, so here when you if you want to use this, you need to use this integration. So 1 by t 0 to t x of t dt. So when you integrate this, you will get this answer as 0. Okay, so finally what we need to do is we need to represent that ak equal to this one for k not equal to 0 and it is equal to 0 when k equal to 0. So this is what you are finding the Fourier representation for any signal.